This morning, we are really fortunate to have Matthew Zimmerman to talk to us about the forward-looking sonar that he and his company have developed and operated. And we here at ADAC are really fortunate in having Matt help us out on a number of tasks that we've been doing, in addition to reaching out to some of our students who are working with ADAC. I'm Douglas Causey. I am the principal investigator of the Arctic Domain Awareness Center. And I think I'll let Matt take over from now. You can explain more about Farsounder, but in case you don't, I've not heard your presentation. It turns out that his application has been used not only for navigation but for scientific research, and I think, Matt, you're going to talk a little bit more about that. So I'll stop talking and let you take over.
Thank you, Doug. I appreciate that. It sounds like there's, from the dings, people trying to join in to this room. I don't know whether they're able to reach in, whether you need to accept them or not, but I hear people joining in.
No, they're on.
Oh, excellent. Okay. Well, thank you, Doug. Thank you, everyone, for taking the time to attend my presentation. Today, I'm going to be discussing 3D forward-looking sonar and how it relates to polar navigation in general, as well as how my company's products and technologies can be applied. First, I want to start off by exploring the question, why 3D sonar? Well, we all know that groundings and collisions cost lives and money. Many of these incidents also cause significant environmental impacts. The polar regions are areas that are difficult to operate in, and the environments are delicate. This means that responding to incidents in the Arctic and Antarctic is a much bigger challenge than in other parts of the world. We're seeing increased vessel operations in these regions, and it's clear that it's only a matter of time before we see the next grounding or collision, which results in a loss of life, high financial costs, or massive environmental impact. And I think we're probably all in agreement also that this engagement in the polar regions will only continue to grow. Therefore, we as an industry and as a society need to develop and deploy technologies to reduce these risks. Part of the problem is that navigation in polar regions is still greatly unknown. Yes, there's been a lot of advances in radar, GPS, electronic charts, satellites. However, those technologies are only part of the puzzle. 3D forward-looking sonar provides the most basic navigation information, which is what is under the water ahead of my vessel. So before we dig into forward-looking sonar, let's define some terms a little bit. Sonar is a very broad term, and let's think about how it relates to 3D forward-looking sonars and how it differs from other sonar technologies and other sensors on board the ship. So as you probably know, every vessel has a standard echo sounder, and these sonars look straight down, and it tells the vessel operator how deep the water is directly below the vessel. But as you can see from this illustration, it does not detect the rock ahead on the seafloor. And every larger vessel has a radar system. This is a sensor operating above the water, and as you can see, this technology still does not detect the rock on the seafloor. Some vessels have a type of sonar called scanning sonars. Technically, scanning sonars can be called a forward-looking sonar since they can be pointed forwards when they're scanning. These systems are primarily designed for deep water fishing and don't provide a reliable navigation picture. As you can see from this illustration, they also can't detect the rock on the seafloor. So from a navigation point of view, to be an effective tool, a forward-looking sonar needs to have a wide field of view with a fast update rate and be capable of sensing from the seafloor all the way up to the sea surface with a single ping. So in this illustration, we show that a navigation forward-looking sonar can detect the rock on the seafloor. And this is exactly what Farsounder's unique technology can do. So let's take a moment to see what our sonars are capable of. Here's an example of our product's 3D sonar display. We generate a complete image ahead of the vessel to navigationally significant ranges with a single ping. The idea of this capability is simple. However, the development of this capability was not easy. I'm a founder of this company and have been working on the development of our core technology since even before Farsounder was born. And next month, we will be 20 years old. So our technology has been under development for over 20 years now. And today we have a true 3D sonar product, and we've been shipping our products to customers all around the world since 2005. Our customers use our products to avoid a wide range of navigation hazards, including, of course, icebergs when navigating in polar regions, large whales, rocky pinnacles, shallow sea bottoms and coral heads, lost shipping containers floating at or below the sea surface, and other unmarked obstacles such as submerged breakwaters. Our products are intended to provide the vessel operator with a clear picture of what is under the water ahead of the vessel. Farsounder sonars operate at navigationally significant ranges and can provide a complete three-dimensional image with a single ping. These systems can map the seafloor out to at least 8 times the depth of water below the transducer module, as well as detect in-water targets out to the full range of the sonar. So let's take a quick look at the software display that's found in all of our navigation products. In this video clip here, we see the seafloor as well as a number of bridge pilings ahead of the vessel being detected by one of our sonars. The seafloor has its color mapped to depth, where blue is deep and yellow is shallow. On the left-hand side of the screen, we see our chart overlay display. Everything inside the sonar's field of view, i.e. that pie wedge, is real-time information ahead of the vessel. And this display also includes a bathymetric trail to the side and behind the vessel of where we've just been. We call this our local history map. On the right-hand side of the screen, we see the same real-time sonar image ahead of the vessel inside our 3D sonar display. The user can rotate this image in 3D with a mouse or trackball, and a 2D slice through that 3D image is shown at the bottom of the screen in the profile display. The user can select any bearing they choose using the profile selector, and that's the white plane shown in the center of the 3D image. We use this same software across our entire line of navigation products, and our navigation sonars are installed on a wide variety of vessels. These products consist of the Argos 350, Argos 500, and Argus 1000 sonars. The primary differentiator between our models is range, hence our cleverly named product models. These 3D forward-looking sonars have a maximum operating range of 350 meters, 500 meters, and 1,000 meters respectively, so out to over a half a nautical mile. The maximum operational speed and field of view also varies according with each model, as you can see on the chart. Each of the Argos series sonars use a specific in-water sensor, which we call the transducer module. The primary difference between these units is the number of elements in their receiver arrays. The more elements result in a higher resolution sensor, which is capable of operating out to longer ranges. The Argos 350 transducer module has a receiver array with approximately 50 receiver elements. The Argos 500 has approximately 100 elements in its array, while the Argos 1000 has a receiver system with approximately 200 elements. All the Argos sonars utilize the same sophisticated sonar processing and display software, which we just saw, and the same type of inboard equipment, which we call the power module. We supply a cable that's used to connect the transducer module to the power module, and it features an underwater wet mateable connector. This allows the transducer module to be installed or removed by a diver. So now that you've been introduced to what our technology and our products do, let's take a few moments to talk about how they do it. Other forward-looking sonars are based on 2D technologies, a lot like a radar, but underwater. These types of sonars can only generate an image of signal levels versus range and angle. In this example here, we took real signals from a single ping from one of our sonars and processed them with traditional 2D beamformer processing on the left and our 3D beamformer processing on the right. This ping was transmitted with the vessel approaching alongside a commercial pier, and in the 2D image, we can see strong reflections corresponding to the location of the pier that I've marked here with this dotted line. However, with a 2D sonar, we can't determine how deep the object is, only where it's located. In the 3D image, we can see the same feature in the horizontal slices, as well as the seafloor ahead of the vessel in the vertical slices like we see here. We can also see the raised structure of the pier wall, showing it extending from the seafloor all the way up to the surface. As you can see, the beamformer processing output is pretty complicated, and it takes some effort to interpret the display. This is why we've developed further processing stages, which we call target modeling. These basically extract relevant 3D information from the 3D data. On the right, we now see the standard 3D output from our system. In this case, the target was a pier wall and clearly visible above the water. However, if this was an underwater obstacle, traditional 2D processing would not be able to tell you if the object was deep and therefore safe, or shallow and therefore dangerous. There are a number of applications relevant to polar waters that can be addressed with this existing forward-looking sonar product. These applications all relate back to that basic question: what is under the water ahead of the vessel? Some hazards are stationary but not charted. We know we have tremendous areas with little or no chart data. Some hazards are transient, like ice or boulders pushed by ice. Some hazards are poorly positioned relative to the vessel, whether the surveyed location is wrong or the vessel's current position is not accurate. A known hazard may not be where the vessel operator thinks it is. And of course, some hazards are new. Post-disaster, debris from land or other ships or drilling rigs, etc., can be introduced to routes that were previously clear and now have become unknown. You've probably noticed that most of these applications are not unique to polar regions, other than the ice, but they certainly are amplified in these locations. 3D forward-looking sonar, when used in conjunction with the other standard navigation tools like radar and ECDIS, can help mitigate these navigation hazards. Of course, we don't want to propose a solution to reduce one type of environmental impact by introducing a new environmental impact. As I mentioned before, the term sonar is very broad. Anything that uses a pressure wave to make a measurement is a sonar. And most legitimate scientists are in agreement that some types of loud, low-frequency sonars can harm marine life. Far sounder sonars are not like these. Our products are out of the range of the great whales, out of the hearing range of the great whales, and they're quieter than a dolphin's own biological sonar. Additionally, our products operate at a lower power output and slightly higher frequency than the most common and accepted commercial echo sounders. We take pride in making sure that our products are environmentally benign. In fact, our early motivations were environmentally driven. Our early prototypes were developed with the goal of reducing whale ship strikes and avoiding oil spills caused by groundings and collisions. Far Sounders offices are located in Rhode Island, and ship strike is one of the leading cause of death for the endangered North Atlantic right whales that make their home off of our coast. We have also experienced a local oil spill that was caused by a barge hitting a rock. By global experiences, this was a pretty small oil spill, but still quite large by our local standards. And these events really help drive the motivation for our product development. And now these products are installed on a wide range of vessels operating all over the world, from hot tropical waters all the way to the cold polar waters. Many of Far Sounders customers have ice-classed hulls and are utilizing our standard fixed mount installations. A few of our customers have full ice-breaking capabilities and deploy our sonar with a hoist. In all cases, these customers rely on their Far Sounder sonar to help them navigate safely. Our customers include passenger vessels, research vessels, yachts, military and Coast Guard vessels, survey vessels, offshore service vessels, and so forth. I want to show you a few examples of how our equipment is installed on various hulls. Here are some vessels with large bulbous bows. The two pictures on the left and right are actually ice-classed vessels. And of course, we can install on vessels with smaller bulbs. The large picture shows an Argos 500 installed on a 62-foot composite hull Nordhaben, and the other two are vessels with medium-sized bulbs and our sonars installed. This is a picture of another ice-classed vessel. This time it's an example of a straight bow with the Argos 500, shown here pretty small in that red oval, installed directly on the center line. Some of our customers have straight axe bows. These pictures show an Argos 1000 installed with a rectangular fairing on the vessel's center line, and this is another ice-classed vessel. And as I mentioned before, a few of our customers have installed the sonar on a hoist. This is useful for ice-breaking vessels and other special applications. On the left is an ice-class yacht with an Argos 500, and on the right is the picture of the hoist from the RSS Sir David Attenborough. They're an icebreaker research vessel, as you probably know, and has an Argos 1000 installed. The Argos 350 is designed to fit inside a standard 10-inch diameter sea chest, so a pretty small installation hoist solution. Besides the real-time forward-looking applications for 3D forward-looking sonar, I also want to introduce you to some of the other features of the technology. Some of these are available today. Some of these are things that are still in development, but I think would be valuable to some of the polar applications. As I mentioned before, our primary focus is real-time sensor looking ahead of the vessel to tell the operator what's there underwater. And our products do include additionally what we call our local history mapping feature. This is essentially a survey of where the vessel has been recently, and it's similar to the output of a standard down-looking survey sonar. This capability is available today, and it's used for retracing a difficult passage through a treacherous route, or perhaps an anchor survey before dropping the hook in an unfamiliar location. The local history mapping capabilities today support about 1 hour of history, and in future software updates, we plan to enable the ability to store and recall more than this 1 hour. And in the future, we even envision the capability to store, recall, and share data across a fleet. So for commercial operators sharing data between all their far sounder equipment, they could now have a huge picture shared across their fleet. Similarly, for yachts, if there are multiple yachts operating under the same vessel management company or cruising club, those far sounder systems could share their data across that fleet as well. Again, reducing the hazards to navigation for all of those participating. Besides our current local history mapping capabilities and those future plans I just mentioned, we also have a program which we call our expedition-sourced ocean data collection program. This is a program that we've introduced to a select number of our customers who are operating in exotic locations and are interested in contributing to science and want to participate in making the system better. Basically, we give them a USB hard drive. It records all of the raw data from the sonar and their other NMEA sensors on board, and we send it back to Farsounder for compilation. Here's a map of some of the data collected by our customers. We've got over 30 terabytes of sonar data collected so far and have about 50 terabytes of drive out in the field currently. We use this data in a number of ways. First, it's part of our continual testing program. As we develop and refine our algorithms, it's great to test different sonars with different locations and different conditions. And a subset of this data is submitted to the NOAA IHO's database through the IHO's Crowdsource Bathymetry Working Group. Farsounder is a trusted node for the IHO's Data Center for Digital Bathymetry, and we participate in the Crowdsource Bathymetry Working Group. All the contributions to the IHO's database are available for public use and are also contributed to the global Seabed 2030 effort. So one question we get is, how does crowdsourced bathymetry become useful to the operators and the global community? Well, here's an example of some data we've collected locally by our office in the Narragansett Bay. and we can clearly see all the major features and navigation hazards detected by the sonar. If this was an area that was not charted or not recently charted, this data would be invaluable because it would allow hydrographic offices to look for discrepancies from their official data, and they could use this to help plan their official survey needs, scheduling their resources, and planning their routes. For those users that want a more capability from the survey point of view beyond our 1-hour local history mapping, we do have a direct integration into the Kinsey product from QPS, and this gets our sonar data into the real-time ecosystem of the QPS ecosystem. So just like any other survey system, they can use far sounder, forward-looking sonar data inside that whole survey suite. And QPS is one of the 3 global leaders for hydrographic survey data acquisition. Another technology area that we're beginning to explore more is unmanned systems. One application of this is of unmanned surface ships is related to smart shipping, and that may be part of Alaska's future. Our current products include a machine interface to our software via a standard Ethernet connection, and this is mostly used today as an interface to third-party ECTA systems, but some of our customers are using the same interface today as a connection into their unmanned surface vehicle control systems. Though this is not a focus of Farsounder's products, we can offer customized solutions for specific projects today. And as USV technologies mature, I think we're going to see more applications for this using 3D forward-looking sonar. And as I mentioned before, this might extend to smart shipping with unmanned vessels, which may be part of how commercial access to polar areas is expanded. One last application of 3D forward-looking sonar that we're currently working on, which relates to the Arctic, is fisheries. A variety of sonars are used today by the fishing industry to help improve the productivity of fishing. However, the vast majority of these products are focused on the localization of fish. That is to say, these sonars are used to help determine where the fish are. Farsounder has been slowly working on adapting our classification algorithms, which we originally developed for diver detection systems, and we now use in our forward-looking navigation sonars. We've been looking to adapting these classification algorithms for fisheries. Our plans are to say not only where the fish is, like is done today, but also what species the fish are. Though this is still in the R&D stage, we've completed some exciting proofs of concepts and are starting to look for partners for these future stages. The benefits of this technology are once again rooted in reducing environmental impact, saving money, and of course, saving lives. So regardless of what answering the question of what should or shouldn't be the quotas of fishing, if we take our existing quotas and we can help fishing vessels avoid bycatch and focus on their target species more effectively, then we'll be able to fish their current quotas more quickly with less damage to the overall ecosystem. If we can save, say, 1 day from a 10-day fishing trip, that translates to lower operating costs and a 10% improvement in safety. Fewer fishing days at sea equates to fewer accidents and fatalities. This is directly applicable to the Alaskan trawler fleet and something I'm really excited about, which could be applied globally, even outside of these polar waters. So in conclusion, owners and operators are really concerned about minimizing risk while navigating. I think it's clear that in the polar regions, this is a huge concern to vessel operators. And I hope I've been able to show you all how Farsounder's navigation sonars can be key contributors to vessel safety and that they're easy to install and use. By helping to avoid collisions and groundings, we can minimize ship downtime, reduce injuries, decrease environmental impact, reduce the frequency and severity of claims, and save a variety of indirect accident-related expenses. All of these things mean contributing to an improved ROI, regardless of whether you are a commercial operator or a yacht operator or a military or Coast Guard operator. Keeping your vessel in operation longer and more safely makes a lot of economic sense. So thank you for taking the time to learn about 3D forward-looking sonar and its applications to polar navigation. Once again, my name is Matthew Zimmerman. Feel free to call or email in the future, but I also have a few moments left to answer any questions that you may have.
Thank you, Matthew. Wow. Well, we do have a few more minutes. Are there any questions from those who watched the presentation? I'm holding myself back, Matthew. All right. You'll have to forgive me for some naive questions because I'm a research scientist. I guess I am fascinated by the range of capabilities that you have now. The Argos 1000 is your most powerful instrument. Are there plans in the future for anything beyond that?
We've started thinking about longer range systems. At the moment, we've actually been focusing on smaller, shorter range systems. And this last year, we launched the Argos 350. Our belief is if we can get more vessels matched up with a product offering that meets their needs at a price and performance point, we can get more vessels collecting data. And as we grow this crowdsource bathymetry ecosystem and environment, not only will we have the real-time needs met for more and more vessels, but we'll be able to share that data across fleets and then potentially in the future even across to non-far sounder operators. So talk about like big data in the marine environment.
Okay, well, why I was asking, I actually was going to go in the other direction because we all are aware that by far there is more small boats and ships than there are large boats and ships, particularly up here in the Arctic. The crowdsourcing and data access right now is available, right?
Correct. We have local history mapping that's part of our current products that provides a 1-hour history inside our software. And for our customers that are part of our ocean expedition ocean data collection program, we provide them hard drives that they're able to share data they recorded with us, and we submit a portion of that to the IHO and NOAA's Crowdsource Bathymetry Working Group database.
Okay, I can foresee a time when this is going to be the archiving, accessing, and availability of this data is going to be far beyond what your company can promote. So I'm not aware of anyone stepping up just yet, but this may be something that, for example, NOAA may want to get involved in.
Sure. I think there's a lot of excitement that can be happening in the future with crowdsourced data, whether it's bathymetry, whether it's other environmental information that's valuable. I think a lot of the community, though, doesn't yet understand what is the business model for operating and handling this information. So we're in a unique position in that our core value proposition is the real-time, forward-looking information ahead of the vessel. And if you have that capability from the far sounder, you also get the historical data basically at no extra hardware cost. So we've incentivized our customers to use the equipment already. And what we're doing now with our ocean data collection program is trying to figure out how to handle all this data. How are we going to operate with it? What is the business model as we expand? And partnering with organizations like NOAA, IHO, other organizations are things that we are excited about. And I think looking at this crowdsource community as a whole, I don't think the marine community quite knows what the business model is, but there are a lot of people that want to try to be part of it as we figure out what what that becomes.
Well, thank you, Matthew. We have run out of time. A very fascinating presentation, and we all are quite grateful that first you were able to present for us, and second that you enabled us to record your presentation. So again, any questions about details about Far Sounder, please contact Matthew.
Thank you, Doug. Thank you, everybody.